Okay, so this will be the second part of electric field lines we just discussed in the last video. That was first part. So in today's video we are going to see electric field lines again, but this will be the part one. Some like a lot of stuff is remaining we need to discuss here. So electric field lines are simply a space or a region which you can look into this picture. It's a region around the charged body in which another charge experience a force that electrostatic force between them. I just discussed the definition and a little stuff in the last video with the diagrams, but in this video I'm just going to tell a little more about it. I will just tell you if here we have the one charge and here we have the second charge. Okay, so if these both are very much far from each other, so there will be no like experiences of force or no experience of charges just because these are far. Okay, I did not tell in the last video, but here I'm just telling you if the charges are too much far from each other, this means they don't have any kind of repulsion or attraction. This means the charge is not experiencing any kind of like the charge not experiencing not any attraction, not even any repulsion. Okay, so now we need to look into as we know electric field lines are imaginary lines which we have not seen in our real life, but we imagine, whereas magnetic field lines are real. Okay, so I'm gonna just write. Okay, so electric field lines formula is simply E. Like we can just say electric field lines are denoted by E. So E is like electric field lines, whereas we have the force into charge. Force into charge. This is force, man. So this would be equal to, we can just simply write F upon charge is denoted by Q. Okay, and there like a new force unit is Newton, whereas charge unit is Coulomb. Okay, Coulomb. So we can just say Newton per Coulomb is the SI unit. Newton per Coulomb is the SI unit of electric field lines. Okay, and this is a vector quantity. How it's a vector quantity? Vector quantity. This is vector quantity. How you can look into this picture. We have the charge. This means they particularly have a direction. They will not go like they have a direction. Whereas if they wanna go in the positive or in the negative term, but at least they have the direction plus they have the magnitude, and that's why if they have a direction, we can just call this as the vector quantity. So this means electric field lines are the vector quantity. Then I'm gonna just tell you. Positive charge have the fields or that terminates. Positive charge is like originated point, this is originated point, and this is terminal point. Originated, which means from which it have been derived or it have been started. Okay, whereas negative charge, which means it's a terminated, where they will not embed it more. Okay, so positive charge originated point, which is outward, like the positive would be outward, and this negative charge would be inward lines. Okay, so yes, so I'm just telling you electric field lines and electric field intensity. These both were introduced by Faraday. This was introduced by Faraday. I'm just writing simple. It's F Faraday. Okay, this was introduced by Faraday, and these have the two like cases, or there were two we can say cases. Yeah, that was action and distance, which were action and distance displacement, whereas that was introduced by Newton, which was failed before Newton. It was failed. Then we just get the second one, which was electric field or electric field line, that was introduced by the Faraday, which is still working. We can just say it's a latest research as well, electric field lines and electric field. I'm not writing right now, but you may get it easily. So I'm just going to write few important points. It's originated positive, or terminate negative. It's have SI unit is Newton per Coulomb, Newton upon Coulomb. Okay, it's imaginary lines, and they have